Alright, so most of you are coming to this class from having taken something like our Foundations course. And as you know, in that course we covered a lot of, an overview sort of chemistry. A lot of different things, a lot of different areas. But here we move on to organic chemistry. And so I want to start off by first sort of broadly defining what organic chemistry is, why it's so important to us. And then we're going to spend a little bit of time reviewing some of the important things that we covered in Foundations. We're not going to review all of it, but there's just a few things I want to touch on just to make sure we're up to speed and that we sort of remember those things. So where to start other than the beginning? What is organic chemistry? Well, we have something you've seen many times before, the periodic table. And as you recall in Foundations, we looked at many different parts and many different elements that we find on the periodic table. Well, in organic chemistry, we're going to look at one of those elements. We're going to focus on carbon. Why carbon? Is carbon somehow more important than the other elements? Well, the answer quite simply is yes. In fact, some organic chemists would tell you that the periodic table would more accurately look like this. And so what we're saying here is that organic chemistry, first of all, is the study of carbon-based compounds. Now we will also see some other elements involved. As you can see, we haven't gotten rid of hydrogen or nitrogen or oxygen or some of the halogens, but we've replaced almost everything here with carbon. And again, that's because carbon is so much more important than all of our other elements to us. So how can we define organic chemistry? Well, very simply, it's the study of carbon-containing molecules. Again, that's not to say that it's only carbon. We'll see plenty of carbon as well as hydrogen, nitrogen, oxygen, phosphorus, sulfur, and sometimes the halogens. But every organic molecule that we deal with is based on carbon. And carbon becomes the focal point of the element. It's the building block that the compounds we will study are made up of. These other elements, will all be important contributors. But again, they're attached. They're not the focus of the molecule. So why carbon? Well, quite simply, organic molecules make up all of biology. Everything inside us physically is an organic compound and control pretty much everything we do biologically. In addition to that, so many things that we encounter on a daily basis are organic molecules. So take a moment maybe and think about that. Think about some places in your everyday life where we might find organic compounds. So what have you come up with? When we talked about biology and any major class of biomolecules, whether it's proteins, lipids, DNA, carbohydrates, these are all organic molecules. They're all carbon-based compounds. But biology is not the only place that we get these things. Plenty of other sources, plenty of other things that we're familiar with are organic-based compounds. And if you think about drugs or pharmaceutical compounds, how many drugs do you know of that are not organic molecules? In fact, I only know of, off the top of my head, one common pharmaceutical compound that's not an organic-based molecule. Anyone know what that is? If you're familiar with lithium, the medication that's commonly used to treat bipolar disorder, it's actually the salt lithium carbonate. And so that's actually not an organic compound. But it's one of the only ones out there. If you think about your clothing, most of the fabrics we use are organic. Our fuels, plastics, all of these things that we use every day and don't even really think about. Because this list, I've put 8 things up here on this screen. We could put 20 more. And we would see just one thing after another that we don't even think about, that we use every day, is an organic molecule. And so that's why organic compounds are so important to us. They are literally everywhere and in everything that we do. Now, organic chemistry wasn't always defined in this way. And if we talk about ancient history, now using that term ancient history is always relative, because if you go into your history class and say that you want to talk about ancient history, at that point you're probably talking about thousands of years ago. In organic chemistry, if we say ancient history, we're probably talking about the 1800s. And so until the 1820s, organic chemistry was defined as being the study of what they called living compounds, or compounds that contained a living force in them. That's kind of a strange definition. Not even sure what they meant by that definition. But largely what they meant was organic molecules were compounds that were derived from, biological sources. And it was in 1828 that a very famous experiment happened. It's one of those experiments that here today we wouldn't think of as being significant. I mean, the reaction itself isn't that interesting. But, close to 200 years ago, this experiment ended up being very significant. And so a chemist by the name of Wohler, very, very simple experiment, at least would seem that way to us. Took this compound NH4NCO. You may remember some of these terms from, previously. NH4 is the polyatomic ion ammonium. NCO minus is a polyatomic we didn't go over in general chemistry, but it's known as cyanate. So what did he do with this, seemingly very simple compound? Well, nothing all that complicated. So when we use this triangle, which is actually an uppercase delta, this signifies heat. And so what he did was he heated this compound up. As a result, and if you count the atoms, you'll find we've got 2 nitrogens on both sides, 1 carbon on each side, 4 hydrogens on each side. So literally the atoms in ammonium cyanate rearranged into a new structure. One of the other interesting pieces is, if you think about this, ammonium cyanate is an ionic compound. How do you know that? Well, it's 2 polyatomics that are joined together, the ammonium and the cyanate. But when it rearranged, it actually formed a completely covalent molecule. What is that covalent molecule that it formed? It formed something known as urea. And urea was a compound that even in 1828 was known. Not only was it known, but its source was that it was found in urine. And so this experiment was the first time someone had ever taken a so-called inorganic or a non-living compound and made it into one of these so-called living compounds. And for everything that they could see, there was no difference between the urea that he had made in the lab and the urea that could be isolated. So what this meant was that this original definition of living compounds was no longer sufficient. And it would be a number of years, but eventually Kekulé came along and redefined organic chemistry as the study of carbon-based compounds. Alright, so why do we study organic chemistry? Again, as we've talked about, the biology is pretty important. And why do we differentiate between organic and inorganic compounds? Well, in general, carbon-based molecules have mostly covalent bonds. If you recall, in foundations, we saw a lot of ionic compounds. Most organic compounds have low melting points, and generally they're not soluble in water. Alright. So why study organic chemistry? Well, most of you are probably answering right now because I have to. And hopefully by the end of this semester, we're going to show you some of the usefulness of organic chemistry and that it's more than just a class that you have to take. But I'm going to start with a story. So this isn't something that we'll do in a class like this, but one of the main reasons people study organic chemistry is, at least from my perspective, this is what I loved about organic chemistry. If you look at this molecule on the left, Taxol. Taxol was discovered quite some time ago, at least 30 or 40 years ago, and was found to be very, very useful as an anti-cancer drug. There was just one problem. If you take a 100-year-old yew tree, the bark of this tree will give you approximately 1 gram of Taxol. Now, that's kind of a problem, isn't it? Not too long before you start running out of 100-year-old trees. Because if you start taking all the bark off the tree, what's going to happen to it? Of course, you're going to kill the tree at that point. So what were the other options? Because it was found to be very, very helpful. Well, chemists said, we can make it. And so a research group down at Florida State became the first group to successfully synthesize Taxol. And they found that it took 46 steps. So by 46 steps, we mean 46 sequential reactions. So step 1, take that product, do step 2, take that product, make step 3. And one of the problems with synthesis when you're working on that kind of scale is they found if they started with 1 kilogram of starting material, they only made 81 grams of Taxol. So very, very inefficient. So what was the alternative? Well, now we see this other molecule on the right, 10-diacetylbactam 3. This is also found in a yew tree, but comes from the European yew tree. But it's found in the needles. And so if you think about that, you find something in the needles, well, you don't kill the tree by getting its needles. That's a renewable source. And if you compare their structures, you'll see that this whole major part of Taxol is already there in 10-diacetylbactam. So what were they able to do? They figured out, well, we can get diacetylbactam from the needles of the yew tree, and by using organic reactions that were known, we can convert it all the way to Taxol. And so that gave scientists and eventually medical field access to enough Taxol that it could be used to treat people. How important is it? Well, at its peak in around 2001, Taxol had a little over $1.5 billion in sales. So pretty important compound. But without sort of that combination of nature and organic chemistry, would never have been able to use it.